Hi, everyone. Thank you for attending today's webinar, Dirt, Steel, and Equipment, Capital Considerations when Designing Solar Layouts in PV Farm. I'm Kelly Pickerel, Editor-in-Chief of Solar Power World. And before we get started, I want to go over just a few items. You can view the slides for today's presentation in the resource window on your screen, and you can submit questions related to today's webinar in the Q&A window. If we do not get to your question, our presenters may reach out to you afterwards. And finally, if you're watching this webinar on demand, you can still use all of these features, including sending questions to our presenters. So let's get started with today's webinar on utility scale project design. I'd like to thank PVFARM for sponsoring this presentation. Today, we're going to hear from Maxim and Ben from PVFARM, and now I will turn things over to them to get us started.
All right. Thank you, Kelly, and thanks to Solar Power World for having us. This is great. We like doing these things. Today we're going to talk about dirt, steel, and equipment. I'm Ben. Maxim's on the line here, and we'll hear from him shortly. We're going to talk about primarily the capital considerations. There's obviously a lot of different pieces to the optimization problem, especially at utility scale. We only have an hour here today, and we want to get to some questions, so we're not going to have a chance to get through every aspect of optimization, but we're going to focus on these three aspects. So as we know, solar design, pretty much any design, is really a balancing act. In particular for utility scale, we're talking about primarily four different things. We're talking about energy, as the output, obviously. We're talking about the electrical side, how everything connects together. And then we're talking about the equipment, what is going to hold the modules, support them, facilitate all of that energy collection, and then the civil and the earthwork. And today we're really focusing on these three main components: the dirt, the civil work; the steel, which is how the equipment is sitting on top of the civil work. And when we look at this, you have sort of this pie chart. We have all these different costs that fold into this. Now, there's obviously, if we're optimizing sort of for minimum costs, that's one optimization problem. We may have a tolerance for costs to be able to extend budgets for, let's say, higher energy yields down the road, right? And we also, as we'll see with a few examples that we'll go through today, we may actually have almost cost parity, but it's going to give us really within that set. Let's say we have two different designs, cost similarly the same. There's probably a lot of other implications about value that those projects or considerations that those projects may want to take into place. So with that, I'll turn it over to you, Maxim.
Thank you, Ben. So we will start with capital cost optioneering, and we're going to use kind of average size project. Not average size, it's 250 megawatts DC approximately. And the only way to understand the cost fluctuations or cost optioneering is to actually run a bunch of simulations and to calculate the costs, right? So we prepared quite an interesting example. Basically, we picked a project and generated layout 245.7 megawatts DC, same amount of modules, same amount of trackers, same trackers, right? And so then we decided to play around those main components, namely dirt, steel, and equipment, right? And so we decided to play with the parameters such as gradient window, rigid or terrain following trackers, binning piles, no binning piles, running gradient globally or locally. And so we just wanted to see how the same project can be cost differently, right? So you can see here on the slide 5 options, and basically you can see that the first one, gradient window 0 feet, rigid trackers, no bin classes, global net balance. Then the second one feed gradient window, rigid trackers, no bin classes, global net balance, right? Etc. So all those, and what was really fun about this experiment is that the basically the cost varies really, a lot. So we have the most expensive option, 98 millions, while the least expensive option, 88 million. So that's around 11% simply because of the choices we make during design, right? So I will jump back and forth in between this slide and then the next one, because we actually will see how the cost fluctuates in terms of cost of equipment, cost of dirt, steel, and the basically total dollar per watt, right? So if we will go back for a second, we'll see that the option number 1 is different from the option number 2, simply because of the gradient window. So we can see on the slide, second one, we can see that the gradient, because of the gradient window, the dirt went down from 30 to 27 millions, but still went slightly up. And so while having the same cost of the trackers, simply because we use the same amount of them, we basically have the same cost of trackers, and the total cost or dollar per watt, as you can see for the second option, is much better, right? So if we will go back for a second and we'll compare the option number 2 versus option number 3, you'll see that we actually start using basically terrain following trackers, and same gradient window, same gradient strategy, but just changed the way how the trackers follow terrain. And what it changed is that steel, it's almost the same, right? It was 7.1, 7.03, but the dirt went down by a lot, right? But we shouldn't forget about the fact that equipment became also more expensive because terrain following trackers more expensive, but on overall balance, it still gave us a good $0.368 per watt. Right, so let's go further and see what else we've done here. So then you can see here, again, the same gradient window on option number 4, same terrain following trackers, no bin classes, but we run local net balance, right? So meaning that we basically separated site into chunks and run net balance optimization, gradient optimization independently in those chunks. A little bit later on, Ben will explain in details what it means. So what actually changed here is that you can see that steel is actually the same. It's the same terrain following trackers, right? So the same cost, but steel went down, right? So, and the steel the same, but the actual dirt or gradient went down simply because we were a bit more efficient in terms of boundaries, and we didn't need to move the dirt from like top right corner into bottom left corner. So we won a little bit of dirt moving, not a little bit, like 2 millions, right? And it makes this option quite juicy in terms of dollar per watt. You can see quite high benchmarks here actually, and quick comment on this, because we love doing webinars, as Ben said, and we picked quite a challenging project for this one. So it's a lot of earthwork and very bad terrain for solar PV, but this is exactly what's happening in today's world. That's why it's actually even more funnier. So, and then the option number 5, we started doing bin classes. So basically what it means, that basically means that when we run our gradient analysis, when we run our cut and fill optimization, piles are being designed based on minimum, maximum pile reveal and based on embedment, specifically to different areas with different geology, right? But it gives us a lot of many different types of piles. And when you start binning those types before procurement or during procurement, you actually buy a bit more steel. And this is what we actually can see here. So we see that the steel increased, and we also see that the total cost dollar per watt increased as well. So that's the whole point of doing capital cost optioneering and running a bunch of different simulations. And as you can see, again, the beauty of this experiment is literally the same layout, the same number of trackers, the same number of modules, but just different design parameters. And it's not only about like picking a different manufacturer or different tracker, or terrain fallen versus rigid. It's also about like a simple design parameters, simple optimization things like different grading strategy. And this all affects a lot the total cost, and it's very important to take this into account. So now I hand it over to Ben to explain a bit more about those parameters that drive it.
Sure. So thanks, Max. So we're talking about the parameters here. And what we mean by the parameters is really what are those dials, those levers, what are the things that we have control over from a design perspective? We're going to fix some of this, right? Everything, if it's a greenfield site, basically everything's in play. But in this particular case, we're going to look at, again, the dirt, the steel, the equipment, and what are some of the primary levers that we have to pull to move those different aspects of the design around. First one we'll talk about is maybe less. Let's say I hear about this one less, and it's one of the more important pieces to this puzzle. We have here on the left side of the screen, we have a sort of a cross section through a tracker, just as sort of a diagram. We have the undulating terrain below this. So to be able to adhere to my minimum reveal and to be able to keep the embedment, meaning the pile embedment below the ground, we need to cleave off the top part of this hill and probably fill in this valley, and we need to sort of smooth everything out. So one of the main variables that we have to play with here is the grading window. And the grading window is sort of a generic term. It's gonna allow. It's how much are we going to allow for the terrain to continue to sort of undulate throughout the site, and the grading window itself, along with some of these reveals and these minimum requirements. There can be a lot of different factors that go into that. We see sort of an example, and this is again just an example. Your team or your design may have other ones, but this is sort of a diagram of how, let's say, the floodplain, right? The freeboard, all of these different factors that are going to fit into this to make sure that the tracker and the modules are going to stay clear, are going to be able to operate above ground, and that we're going to maintain sort of the structural integrity below ground from the embedment. So combined with those, we can adjust this window. We can allow, we could grade the site completely flat, minimize the pile length, sort of eliminate this whole orange zone altogether, or we can allow a little bit of play. And depending on what's happening on the terrain, those can yield substantially different results. The next one, which we already touched on, sort of those tracker, the table system manufacturer constraints. We're looking at sort of a rigid tracker, a flat tracker situation. There's going to be a sort of slope along the axis of that tracker. That's going to be both to enable it to rotate freely, maintain warranty. These are sort of really important and kind of critical factors that go into that design. We get more into the terrain following. We have the cumulative slope. That's going to be the sort of total slope across the length of the tracker, across the wing of the tracker, kind of manufacturer dependent. And that's the total slope, and then the base, the beta base slope would be the slope sort of between the different piles. And again, there's a little bit of variety in terms of how the manufacturers may specify that, but those things together are going to impact how that tracker can sit on the earth along with the piles, which we talked about previously. So let's talk about the dirt now. In terms of that, if we're talking about a tracker system, they're in the northern hemisphere. They're going to be oriented, hopefully, with south facing, but we're going to be sort of north to south. In those particular conditions, as most of you probably know, we want to avoid sort of shading across the rows. We want those to be sort of free and able to collect the maximum amount of power that they can for the density that the site requires. The east-west slope going to allow that slope sort of moving between, sorry, I was just talking about the east-west and the north-south slope. Again, we're talking about kind of a combination of that slope along axis of the tracker. Now, it's not the same thing, right? Because we can adjust how big these piles are sort of from start to finish. So you can have sort of a wedge shape. You can have a lot of different things happening here. but there's going to be some sort of constraint associated with that as well. That may be from an installation standpoint, that may be from an operational standpoint. There's a lot of things that can drive that factor. Now, within the site also, we have different sort of areas of grading. The white boxes we have would be sort of the tracker grading, the area that's within the arrays and the grading that happens there, sort of the white and the orange here. And then there's everything else, right? You're going to have roads, you're going to have sort of other ancillary parts of the site, and those may need some work as well. We'll call those sort of the scratch areas in this particular case. So the combination of those all together, we start to get a picture of like how we can tune those different dials on the civil side. And the last piece, also related to civil, talking about net balance. Max mentioned this earlier. When we talk about net balance, we're talking about how much dirt, the balance of dirt, that we want to either bring on the site or take off the site. In many cases, we want to use the resources that we already have on the site, so we want that number to be as close to zero as possible. I mean, we also want those different zones to be within a reasonable sort of radius of the equipment, right? A piece of equipment has to carry that dirt. The whole site is not going to be under the same state when we're talking about construction at the same time. So we can talk about the global net balance, meaning across the entire site, how much, what is sort of our net balance. We can also break that down into smaller and smaller areas to help optimize both from an operations standpoint, and in some cases, as Max was describing earlier, this can actually yield higher efficiencies when we apply it that way.
Yeah, so now we're gonna talk about a bunch of workflows. I would say the most popular workflows among the people we work with. Those workflows are related to the topic, right? Dirt, steel, and equipment balancing act, and basically considerations that need to be addressed and analyzed, right? So the first, it's probably very popular and everybody understands this. It's about cut and fill versus piles. So in a nutshell, it's all about actually driving the minimum maximum pile reveal range or grading window, right? So let's say here we have two options, 1.5 feet grading window for our project, basically, and we, we can basically run different analysis for different grading windows. And for example, our project, it gave us basically 1.5 grading window, 93.7 millions, and then 0.5 grading window gave us almost 97 millions cost, right? If we will have a look, what's the difference, right? We will see that the trackers are the same, again, because it's apples to apples, same layout. But then the piles from 17 millions to 16.8, they basically went down for 3.6%. And then dirt, as expected, it went up because like basically the narrower grading window, the more kind of dirt we need to move. And the key challenge in such an analysis is that we always need to consider both aspects, right? We cannot run different grading strategy and then compare dirt and say, okay, this is project better because of the dirt, right? But because it's not enough. In that particular case, like piles can play a decisive role in terms of cut fill versus piles, right? So and the difficulty is that being able to analyze dirt and piles simultaneously is actually the key for such a workflow, right? So let's go to the next one where we will talk about, again, this is a very popular topic in the last, I would say, 2 years. This is rigid versus terrain following trackers. And when you see and when you talk to people, they usually used to, to say and to show the examples where the terrain following trackers, they save like up to 50, 60, 70% of the dirt, right? And it's right, it's true, right? So if we run with the same grading strategy, our project basically same grading window, 1 feet, and then on the left you can see rigid trackers, on the right you can see terrain following trackers. You will see that actually dirt from 28 millions went down to 16, right? So it's significant. It's a lot. It's basically 42%. But it's important to have a look in the other aspects of it, right? So for example, trackers, terrain following trackers, they cost more. So you can see 51.5 against 57 1, right? And then also because on a certain sites, not very complicated. It's like it's not always that gradient window can affect your piles forever. At some point, it's just because your tracker can follow terrain. It's like a serpentine, right? And let's say if it's not too bad slide, terrain following trackers as well can save you a bunch of piles, bunch of steel, right? So you can see here that the piles cost, which is the cost of the tonnage of the steel, as well as the cost of the pile driving, right? So it went down 16 percentages. And so the piles from 16.8 went down to 14.1. So in that particular case, actually, we went down from 97 millions to 88 millions, which quite a lot, right? So it's a 9 millions, but again, it's not that by saving like 42% of dirt, you're actually cutting your cost twice, right? So there are other aspects like trackers and piles, which needs to be taken into account, and that's the whole basically challenge of such a workflow. So
Hey,
let's go
Max.
to the next. Yo.
Hey, sorry to interrupt. Real quick, there's a question just while we're on this slide because it's quick. Do you remember what the beta bay slope was in this example?
So I think I used some kind of quite aggressive numbers. I think I used 4% bay to bay slope change, and then I used 15 percentages cumulative slope change. It's a bit higher than, for example, than Nextracker XTR Pro, but there are manufacturers that can do this. So basically, that was the slope. But it's not only about that, guys. It's a good question, because it's not going to work the same on a different project, right? So not only the manufacturer constraints are important, but also the actual terrain. We saw projects where terrain following trackers didn't give anything, basically, as well as we saw projects where terrain following trackers cut 70% of the dirt that need to be moved. So this is very project specific, and this is why it's crucial to have a tool where you can actually quickly analyze whether it makes sense for your project. That's why I'm just saying that there is no so I cannot give a financial advice, and there is no a rule to follow, right? So you need to have a specific terrain, specific trackers, specific limitations, and run and compare it on a specific example. And it's going to be different from one to another. Thank you, Ben. So we'll go to the next workflow, which is I love this one simply because it's like, it's actually, if you think about the solar PV project and let's say, again, challenging terrain, there are clearly places where trackers are more pricey to build, more pricey to install, right? And the way how to present it is basically to break down the site area into normal cost of the tracker's installation, and then, for example, expensive, and then very expensive. And basically this example where we do gradient capital cost analysis, it actually illustrates that this project had a kind of river here, so we had a very bad very bad terrain around this place. I'm just showing it on the slide with pointers. And basically, the closer we go to this river, the more expensive to install trackers. And you can see it by dollar per watt, which is, again, calculated taking into account equipment, trackers, dirt, and steel, right? It just goes up. So basically, every step forward comes with a higher price. And this is a nice illustration to use when people, designers, EPC contractors talk to clients, because it's just, if you need 222 megawatts DC, right? Are you happy to pay this price? Are you happy to pay this price per watt, right? If you need to squeeze more, so the price goes up, which makes it more expensive, right? So this is basically gradient capital cost analysis, and the way it works is just you run your layout within a specific area, and you just basically got your cost for trackers, dirt, and steel, and then you see whether it makes sense or not to go further, and whether it kind of supports your financial assumptions. And let's go to the fourth workflow, which is about piles bin classes. That's just a little bit of explanation what's piles binning, right? So when we do design, again, we have minimum reveal, maximum reveal, based on many parameters that Ben explained. We also have embedment. Usually, embedment depends on geology, right? And so it might vary through the site. In a different places, it's going to be different embedment. Also, there might be, different piles cross-section because of the scour and many other aspects, right? But when we design piles, we usually end up having like, for the project like this, 245 megawatts DC, we end up having like 70 types of piles. Types of piles, I mean, in terms of lengths, right? Or even like 100 and more. So, but when people build those projects, they rarely want to go more than to more than 20, right? And the less is better. So, and that's why the challenge is that when you design the piles, and I'll jump quickly on the next slide, and I will come back. You actually have a lot of, you have a lot of pile sizes, you have a lot of pile types, and in a way you have quite an efficient design, right? So for example, in this particular case, we run on this project, we got actually 3,783 tons of steel. But then when people, during procurement phase, they order those piles. And when they order those, they take into account constructability aspects, right? And they want to minimize the number of types of piles because it's just easier to procure, easier to build. So, and the way how you actually bin those piles in the classes when you're minimizing the number of different types, it different, right? So because like here we started in the first option with 4 feet pile reveal, and that was our first bin class, 4 to 5 feet, and then we basically went all the way till the end with 1 feet step. So it gave us, not surprisingly, more tons of steel than we originally designed, right? So we got 4,118 tons of steel. And then we tried the bunch of other procurement strategies. And for example, this one, we started with 4.5 feet with 1 feet step. So we got the buckets of bins like you see here on the slide, right? So not surprisingly, but it's not always like intuitively, but it gave us actually less steel. So we ended up having 4,041 tons of steel. So basically, depending on like what's the biggest, where is this, like a size of the reveal where you have the biggest amount of piles, which you can easily analyze using some kind of histograms or charts in our application. And so you can actually choose a strategy which will be the best in terms of you will not, pay extra money for not being, like thinking about this optimization problem. So we ended up in between this option and this option is like around $500,000. So which is a substantial amount of money and worth considering different procurement strategies. So just going back to the next slide, the previous slide, just to explain a bit. So that's the GIF that illustrates how actually pile binning is happening. So we have no bins, 2 bins, 3 bins, and then basically we have piles with different types depending on wind load position, the position of the tracker, different types of piles, and then we can start playing with those. Not only like binning it by the pile reveal, but also optimizing the lengths, right? So yeah, that's about the pile binning workflow, and that's our forward flow. So now I hand it over to Ben to talk about some insights we got in the last couple of months.
Great. Yeah, thanks, Max. So along the lines of some of these workflows, there's some interesting things that come out of this. The kind of key here from an insight standpoint is the results, in many cases, depend on sort of where you start. That may be intuitive, but in other parts of life, but if we're in sort of a practice where we're used to sort of going through the same routines, the additional flexibility of being able to generate and look at lots of different options in a really fluid way allows you to look at different sort of ways of applying that. So we'll look at some of those examples here. The first one is exclusion areas, right? And the kind of key point here is that just because a slope is high doesn't necessarily mean it's unusable. And that's sort of the key takeaway. On the left side here, the design approach was to look at all of the areas of high slope. Those were slopes that we were above sort of the typical range that we were looking for. We grabbed all of those, turned those into sort of exclusion areas, then we worked on a layout around those different areas. That yielded 32 megawatts DC in that particular case. Now, here's a different approach that we took. We actually disregarded all of the slopes, placed all of the trackers across the site, and then we went back and analyzed the trackers that were going to exceed those slopes and remove them from the design. And we got a pretty substantial bump there in that approach, that 37.1 compared to the 32.0. And the real takeaway here is that it's not actually about the tracker. The tracker is a component of it, but the tracker is the component because the piles are connected to the tracker. And when we're looking at these, as I said earlier, just because the slope is high doesn't mean it's unusable, because it really depends on how the piles are landing, where they are on the site, and what sort of variance you're allowing across those slopes. And you can't really know that answer without getting into that next level of detail. That's the piles, that's the lengths, that's even the types of piles if you want to go to that depth. But if you're sort of staying at that top level, you may be leaving some DC, some money, or whatever is associated with that on the table, because you're not quite at the level of detail that's required to do this thoroughly. Exclusion areas, similar deal. It's probably more intuitive, looking at longer trackers versus shorter trackers. Again, taking that approach. When I lay this out, where are the areas that are going to exceed my slope, and I need to remove those trackers because they're going to, exceed the manufacturer's spec or my own specification. In that particular case, with this is a 90 mod, we're looking at that 34 megawatt DC sort of approach here. And when we go to a shorter tracker, we get a lot more flexibility. We can avoid more of those areas, and the trackers can sort of follow that terrain a lot better, and we get a really substantial sort of gain. Obviously, the shorter trackers, we're going to have more piles, more connections, lots of things going on with that design. So we're likely to see some cost trade-off, but it's just one of those sort of examples of what happens when we look at arranging different types of equipment. So moving on more to the dirt side of things, this is a fun experiment we looked at. We spent a lot of time with PVFARM trying to optimize the grading engine so that it is producing results that are really along the buildable scale. And sort of the counterpoint to that is what we'll start out with here on the left. We have the shovel. This is basically a grading strategy for the site. Only 1,000 yards, really net balance there. And 64,000 or 65,000 is sort of the total amount of dirt. Now that's using basically a shovel, like a handheld shovel. We're not going to build a site of this scale with a handheld shovel, of course, but if you're not really paying attention to how that optimization lands in the real world, you're likely going to run into some issues. See that when we expand out to the 12-foot, maybe 12 to 18, kind of depending on the blade size, for that piece of it, for basically a heavy piece of equipment, which would be used for a site like this, we can see what happens to those dirt quantities. And the point is that there's such thing as over-optimization, right? We've all heard the term sort of over-engineer. And what we really mean by that is not that there's anything wrong with the engineering, it's that we don't maybe have the feedback mechanism to look at how this design impacts maybe other costs, or kind of operational things like we're talking about in this example. So when we talk about tracker size, we've mentioned this already, and here's a kind of a case study with an odd shaped site. And we'll look at what happens across those when we start to look at different tracker strategies. So again, we're going to start with rigid, look at sort of 90 mod, 60 mod in the middle, and then a mix on the right side of the screen. And what we can see down here is from a $ per watt standpoint, these are all within the same ballpark, right? They're all fairly close. Some of them are very close. But the game here is that when we start to add in different tracker sizes, So if we go from the 90, you can see this kind of sawtooth along the top. We can see that there's areas we can't quite fill in. That's probably pretty straightforward. And as we go to the shorter trackers, we can fill out the site better. We can get better density. We can fill out more of these areas, and we're able to bring our cost per watt down, down a little bit. Not significantly, because we're also going to pay for it in sort of additional trackers. Right, got a lot more pieces of equipment out on the site. Now, what's interesting, when we mix the 90 and the 60, we're able to actually fit more of that density on there. We're having fewer roads, right? We have longer trackers, some other offsets here, but we're also still being able to use and leverage those shorter trackers to fill in. So while my total cost is higher, my dollar per watt is basically the same, because I'm gaining 6 megawatts DC on this particular site. And taking that sort of to the next logical step, we're going to look at the terrain following trackers, same sort of thing. And the interesting thing here is that the terrain following actually, in this particular case, eliminates the advantage for any of the shorter trackers, aside from sort of the DC bump. But if that's not sort of a priority, your overall cost per watt is really not being helped by those shorter trackers where it was in the previous mod. We're able to, if we look what happens to the dirt, right? The dirt cost, let me just toggle back and forth. We go from 3.6, and we're going to add a little bit more in terms of piles. We're going to have more piles on the 60 mod side. But for the same megawatts, there's really now sort of a substantial difference between the 60 and the 90. And again, if we want to go into that sort of higher DC output here, we're able to, we could leverage this if that's one of the goals for the project. So here, sort of stacking those up, the colors here are indicating how that pie chart kind of fits together. And you can see, when we look at the 90, the 60, the 60 and 90, you can look at that comparison, and you can sort of see, it's not always maybe exactly as we assumed. You need to do the analysis. You need to go through into this level of detail to understand that. We see that all the time. This is a super simple example. We're using 2 lengths of tracker. What happens if you put every potential sort of string length into the system and start to look at how that plays out? There's a lot of different options you have from here. And next, we'll talk more about how we can actually look at this analysis and do some of this, which is this presentation here.
Yep. Thank you, Ben. So yeah, we're going to talk a little bit about how to. So in the bunch of questions we receive constantly, and I will explain how those can be addressed in PVFARM. Maybe even give a bunch of options. So let's start with the first one. Actually, quite popular one: how to avoid north-facing terrain slopes above 10%, for example. Just an example, right? The requests can be different based on the energy considerations, based on clients' preferences, etc. But basically, in the most cases, how people do it today, and is basically analyzing terrain, analyzing surface, finding those slopes, and then creating boundaries, exclusion areas, and then populating layout with trackers, avoiding those areas. That's why one way of doing things. Another way, as we showed it through insights, is actually sometimes is much better to place trackers first, and then basically, because piles, they basically, assuming that you have a tracker limitation like slope along axis 10%, then the piles will be longer than you expect, and then it's going to be a different way to actually look at this problem. And there is no one-way solution, and there is no one particular solution that works better. I think both have advantages and disadvantages, because when you go through from terrain, you might end up having quite diversity in your layout, and you will have a lot of standalone trackers, or small groups of trackers. While at the same time, when you start from actually placing equipment and then doing analysis, you can end up again having some problems and more cut fill, but you will have a more buildable in terms of visually more buildable and maybe electrically more buildable layout. That's again feedback loops. Important to consider a bunch of aspects. Important to find the right balance and understand trade-offs. So that's why we love engineering. So yeah, the next question, again, very popular one. Hear this one particular like couple of times a week. How to avoid the most expensive grading areas. And actually, we don't have like one analysis which will basically tell you how to avoid the most expensive grading areas. So the people usually they can do some kind of visual insights again when they analyze terrain and they see some slopey areas, and then they. But again, I think this approach it lacks the holistic actually consideration, because slopey areas doesn't mean that we necessarily will have problems there. So again, until you put trackers there, you don't know. So, and this is why what we recommend in PVFARM is actually running a bunch of chunks of places. So like you place trackers and then you select different chunks and you just run simulation. You run the gradient strategy. You understand the cut fill implications, and then because we have an adaptive and kind of cost model that works in a runtime, you can get dollar per watt, right? And then you have a bunch of spots with different dollar per watt, so you can actually understand quite scientifically, right? So in a way, what's the worst place? So what's the worst place? And if it's this rare case when you have excessive amount of land and you can avoid some areas, so you will be able to definitely find the area where you don't want to place your trackers because it's expensive, right? So let's go to the next one. Getting slope adjusted pile point plan. Quite popular request and quite popular ask. Again, a couple times a week as usually. So the way how we work is that, you know, we usually generate like a 2D layout and then we make it slope adjusted, meaning we place it on the terrain, right? And so as we place it on the terrain, depending on your grading strategy, slope restrictions, depending on manufacturer limitations, you start getting like basically trackers with different piles and with different reveals. So after that, we can run quickly a binning, right? And then and this is a perfect place where we actually have like I would say design procurement feedback loop, because our binning that we run separately, it can be applied back to the model. That meaning that if you had a pile, let's say 7 feet, let's say you have a pile like you know, like 5 feet in reveal and then 7 feet embedment, and then you decided that you're gonna order piles of the land, and then many piles like 6 feet reveal and 7 feet embedment. So you might decide to buy certain feet piles, right? In that case, that the one that was like 5.7, you will basically make it 5.8. So you will still have your certain feet, and you just will, you know, knock it down to the ground more. So yeah, that's the pile point plan thing. And then let's talk about final grade. And again, the parameters we talked, Ben explained a bit earlier during this presentation is you can define your grading strategy, right? So you can run different, I would say, different grading strategies in different parts of the project, right? So arrays, they have one grading strategy. Then rods, they have different grading strategy. Then you have a catch grading where you need to grade, just you don't have arrays there, but you need to grade it anyway. And so then you also have like equipment like transformers, skids, substations, where you need to grade also with another grading strategy. So the what we have is that those grading strategies, they can be applied independently on one surface. They will adjust your surface, the existing grade, in the final grade, and then the final grade basically, you know, can be exported into Civil 3D, for example. So then, actually, this is my favorite one, modeling basins while optimizing for cut and fill. So we don't design basins, but like if you know the size, you can, you know, bring it in. You can bring them in, and then if you know the amount of dirt you actually need to excavate from those basins, you can actually excavate them, and then you will be like let's say a couple of millions positive cubic yards, right? So, and you will need to use this dirt in order to grade your arrays areas. So it is possible to actually to excavate dirt and then use it to actually to grade your arrays. So that's quite a fancy workflow, but civil engineers, They always ask about this one. Yeah, the probably last how-to for today is basically about hydrology. So the fun part about working with the civil aspects is that, whether it's terrain, it's surface, right? Then water, flood, let's say 100-year flood plain, it's also surface. So then some scores or like scours or some any other things, it's also surfaces. So basically when you're working with the layouts, um, you can actually bring as many surfaces as you want, and based on specific parameters like elevation or based on slope, you can actually start creating boundaries. Or like it's like a cuts of the surface, right? And as you have boundaries, you can start avoiding those and run grading, analysis in the areas outside of those boundaries, or you can start applying different grading strategies. And again, when I say grading strategy, I mean, let's say if you have a floodplain, I don't know, half feet, right? And and then your pilot wheel will be higher in that area because you cannot allow your module to touch the water, right? So you can find this area by uploading like a flooding plane surface and then run a gradient strategy with higher pilot wheel in that specific area. And then for the rest of the site, we can run a gradient strategy with a normal pilot wheel, right? So that's how we take hydrology into account. So that's basically my last how-to for today. We were going to show a product quickly, but we don't have time, and I'm pretty happy with this. Don't like showing live demos on that environment. So we will hand over to questions, and we appreciate, guys, your attention and appreciate your questions. We saw already many good questions in the chat, so let's go through them.
Yes, okay, thank you. Yeah, we'll get right into the Q&A portion of the webinar. You can continue to submit your questions in the Q&A box on your screen. Our first question will be, what sort of outputs does PVFARM create, and could they be used for design in CAD or Excel, anything like that?
So yeah. Ben, I'll take this one. So yeah, the deliverables we have. So first of all, final grade terrain can be exported into LandXML or DM or GeoTIFF. So basically it can be uploaded into AutoCAD or Civil 3D or any other tool, right? So then the layout, we can convert it into DXF, which can be opened in AutoCAD. All the project metrics, all the information related to capacity, to metrics, to basically quantities, to the cost, it all can be imported or exported into Excel spreadsheet. So yeah, we try to support all classic roads in terms of data flow, because we know what tools engineers use. So yeah, everything designed in PVFARM can be exported in the other software products, basically, like Civil 3D, PVCist.
Okay, perfect. Someone is wondering, is the best way to analyze whether the site could benefit from terrain following trackers just to run examples in PVFARM, or is there a way to analyze the site's slopes in some other way without equipment placed?
Ben,
Max, you want to take this one?
Yeah. Oh yeah, I can. Yeah, absolutely.
Yeah, go for it.
I can go. Yeah. So I would say there is definitely a proxy, right? So we can, at least from experiments we run, there is a proxy of slopes, and you can, generally speaking, experienced civil engineer can actually see the slopes, see the surface, and can give you quite a good prediction in terms of like whether it will make sense to use terrain following trackers or not, right? But the problem starts when it's actually not clear. So, and when it's not clear, the only way to actually to know for sure is to run some simulation and to see some numbers, right? And also gut feeling is a good thing, but sometimes you need to reinforce decisions with numbers. And in that terms, I would still say that the most accurate way of actually answering this is to equipment need to be chosen, or at least you need to have an idea what trackers you're going to use. Because like imagine like when we analyze slopes, it's like basically slope per 1 unit of length per 1 foot, right? but then on the side, we're going to use like a tracker's 300 foot. So, and then if it's terrain following, it's going to go like serpentine within a certain restriction. So it's like it's not entirely different, but it's still, there are two different analyses, and we would recommend to go through both. Yeah.
Okay.
For sure.
How can someone get a license or try PVFARM?
Get in touch with, there's a QR code earlier here. Reach out to us. Our website is pvfarm.io, and there's a number of ways to sort of connect with us. We'd be happy to talk more.
Okay. Obviously, we talk a lot about trackers, but is PVFARM capable of running fixed tilt panels?
Yep. Yeah, we accommodate a number of fixed tilt systems. There's a lot of variety out there in the fixed tilt world, but PVFARM does work. All the workflows that we're looking at today work just as well with fixed tilt systems.
Okay. Someone is wondering, can you put a set layout of trackers and pile designations into the software?
Max, you want me to take that?
Yeah. So you can put layout, and I would say you can define the piles for wind load type of the tracker. So let's say if you have a layout and it has, let's say if it's from a wind load standpoint, if you have like exterior, interior, edge trackers, and let's say if your piles are set well in terms of like per type of the tracker, so you can bring it in. So but the piles will be quite manual and painful, but the layout is fairly easy. So the way how we bring layout in is basically you have CAD DWG file format, and so you have your blocks in this CAD, right? And so we simply require to have some bounding box or something that we will understand the length and the width of the tracker. And then as you upload the DWG converted into DXF in the PVFARM, you will be able to match your rectangles or blocks from AutoCAD with the trackers in PVFARM. So let's say if you will set it up correctly, so you will just basically have like perfect match in terms of like trackers and pile position, like a perfect match. But then if you're talking about like specific pile lengths, that's going to be a bit challenging. Yeah.
Okay. We have time for just a few more questions. So remember, you can submit your questions at any time in the Q&A box on your screen. Next question about like how long does it take to run these types of simulations within the program?
I would say,
Yeah,
go ahead.
Yeah, go for it.
Okay, cool. So let's say if you're talking about this complicated terrain to 45 megawatts DC project, running gradient strategy, and this is quite accurate terrain model. So running cut fill analysis for the whole terrain would take around 1 minute. Then I would say, like generating layout, I would say, like below 1 minute. So then running gradient 1 minute, and then playing with piles and basically export. I would say actually the generation is the easiest part of the process. You can do everything in like a couple of minutes. And then let's say if you want to consider like 5-10 options, you will need to run them like a couple of minutes each. And so then you can compare those. So basically like the first slide where we were talking about cost fluctuations, running 5 options took me like 15 minutes. And but then if let's say you want to bring terrain into Civil 3D, it might take you like 40 minutes to bring such terrain into Civil 3D. So the export is tough, but the actual like automation is quite fast on our end. Yeah.
I was just going to add on to that. I think where we see people spend a lot of time is in the analysis piece. So the simulations, getting these different scenarios built out is pretty quick, and where instead of folks spending sort of time building out those scenarios in the first place, they're getting the scenarios much faster and putting that time into the analysis, which is what we focused on here.
Okay. Yeah, and then I think this will be our last question. What tools did you use for all of these analyses?
PV Farm.
Yeah, yeah, that's the only one. We didn't actually use any. Yeah, we didn't use Civil 3D. We didn't use any other tool. We used only PVFARM. When we showcased how to do the final grade, we actually converted the final grade from PVFARM into Civil 3D. But for all the calculations and all analysis, cost, we have an adaptive and cost model which which is working in runtime. And yeah, so we used purely PVFARM for those.
Perfect. Okay. Well, that is all the time we have for questions today. If you have additional unanswered questions, please feel free to contact our presenters on your own. And as a reminder, this webinar will be shared with all registrants, so you can view it again at your convenience. So I would like to thank our presenters for being here and PV Farm for sponsoring today's webinar. And thank you to everyone for joining us today. I hope to see you at more Solar Power World webinars in the future. Thank you.
Thank you all.